All right, so this is the last section, Section C in AP Classroom, and you can see that there are a lot of videos that you might want to go look if anything here is confusing, okay? So the first thing that we're going to talk about are lurking and confounding variables. And so we have something in stats called an extraneous variable. So in your algebra classes or pre-cal class, extraneous is something that doesn't work, right? So we get a variable or we get an answer and we plug it back in and it doesn't work. And so what happens here with an extraneous variable is it's not one of the explanatory variables in the study. So remember, our explanatory variable is going to be down here on our x-axis. So it's not an explanatory variable in the study, but is thought to affect the response variable. So there are two types of extraneous variables. The first one that we're going to talk about is confounding. And a confounding variable is a variable that is present in an experiment. This is super important. It's present in the experiment. It's tied to the explanatory. So the explanatory affects the response, but the confounding also affects the response. So it's present in our experiment. And it's difficult to separate from the explanatory, so we don't know if it was part of the explanatory or if it was confounding. So it's something that just kind of happens and we don't know if it's part of the explanatory or something that happened outside of the experiment. So here's an example. So what we see here, it says we want to test fertilizer in our garden to see if it makes a difference in the number of peppers we grow. We put our current fertilizer in half of our garden and new fertilizer in the other half of the garden. On the side we planted the new fertilizer, the peppers will get full sun, while the side with the current fertilizer, the old fertilizer, will get shade. At the end of the experiment, the side with the new fertilizer grew the most peppers. So really, what are we testing here? What we're testing here is the new fertilizer. We want to test if the fertilizer in our garden. So we're testing this new fertilizer. So what we need to know, the experiment says the new fertilizer side grew the most peppers. Well, is it because of the new fertilizer, or is it because it got the sun and the other side got the shade? So what we see is that the sun is a confounding variable. It could have affected our experiment. We were only testing the new fertilizer, but because we had a change in the sun, it was confounding because that really could have been why our peppers grew, okay? So the next part says, how can we fix this environmental design? So what we could have done is taken our plot and said, okay, we're going to do old fertilizer and new fertilizer, so instead of doing half of the area, we're going to do a quarter of the area, and then that would get shade, and then the other part of that would get sun. So it would look more like this plot. So we would take and split it in half and do old and new in shade and old and new in the sun. And so what we have done is we've split the area so both receive shade or sun, right? So many confounding variables can be controlled in an experiment through blocking. So that's what we've done here. We have blocked this so that we're able to test everything that we need to see. All right, so that's confounding. The other variable that we're looking at here is a variable that's called lurking. And I know that y'all high school kids have a different term for lurking. You know, if you're stalking somebody, you're lurking on somebody's page. Well, this is kind of the same thing, if you want to know the truth. So sometimes it's called the common response. It's a variable that's present in an observational study that's driving each of the two variables, making it appear like there's some association between them, right? So this is kind of what it looks like. We have this lurking variable, and it's affecting the explanatory variable, and it's affecting the response variable, all right? So the important thing about a lurking variable is that it is unmeasured. Okay, so here what it says. The data was examined on the amount of damage seen from a fire. So they're going to look at the data in dollar amounts and the number of firefighters that responded to the fire. So probably something like this. So the number of firefighters and the cost associated with the fire. A researcher concluded that the more firefighters that responded to the fire, the more damage occurred. They suggested that the least number of firefighters should respond to the fire. So let me read this again. A researcher concluded that the more firefighters that responded to the fire, the more damage occurred. And so they suggest the least number of firefighters should respond to a fire. So what they're saying is, as you have more firefighters out here, you have more money, more costs associated than if you have a firefighter here. Well, what's happening is we have a lurking variable right here, and the lurking variable is going to be the size of the fire. So the size of the fire is going to drive how many firefighters you have, and it's also going to drive the cost of the fire. So the bigger the fire, the more firefighters, and the bigger the response. So this would be something that is a lurking variable. It's not measured like confounding with the sun. This is just something that's kind of matter of fact, right? So we have this experiment that we have right here, and it says, in a study involving 4,700 children, researchers from the Children's Hospital found those children whose mothers smoked during pregnancy were more than twice as likely to develop ADHD as children whose mothers had not smoked. Explain why confounding makes this unreasonable to conclude that a mother smoking during pregnancy can cause an increase of ADHD. So let's think about this. So what we're saying here is smoking mothers, and this is ADHD, and what the experiment says is the more you smoke, the higher your chances of ADHD are. But here's the problem. So what is confounding on this is what if she just had bad diet and that the diet led to ADHD? Or what if she did take so no prenatal vitamins? And the prenatal vitamins led to the ADHD. So we've got other things that are happening within our experiment that we can't say is causing smoking to give you ADHD. Now, this is really important. So when we're talking about this, we have to show, so you have to justify the explanatory and the response variable when you're dealing with confounding. So an example of this would be, in fact, let me write this down. I'll grab a piece of paper real quick. What you want to say, if this is a justify statement, you would say, it is possible women who smoked had, I'm just going to say, had a less healthy diet and eating poorly during pregnancy. I get the whole context in there. Increased the risk of ADHD. So when you have a confounding variable, you have to go in and you have to do your justify. So here's what happens. So women who smoked had a less healthy diet. So this is my explanatory. And eating poorly during pregnancy increased the risk of ADHD. This is my response. So with confounding, you have to have both. You have to justify your explanatory and you have to justify your response. So you're basically stating both, that this could have affected your response. Okay? All right, let's keep going. So researchers surveyed over 15,000 people in Europe and Australia and found that those who lived within 1 kilometer of the coast are 22% more likely to report a very good health than those who live more than 1,000 kilometers from the coast. So here's what we have. We have the distance to the coast, and that is going to be their health. Is going to be on this axis. So is this an experiment or an observational study? Well, this is just an observational study. We're not changing. We're not doing anything here. We're just going out and we're surveying people. So this is just a study. If we said we're going to move people to the coast and we're going to move people inland and we're going to do something, well, that would be an experiment. But this is just a study. So explain the explanatory. Well, the explanatory is going to be the distance to the coast, and the response variable is going to be their health. So based on this study, is it reasonable to conclude that moving to the coast will improve your health? And so obviously we would say no, this is not the case. And so why is that? Well, we could have a lot of different things that help us, all right? So we've got all of these lurking variables in here. So some of our lurking variables might be just your general health. Just your general health. It could be your job. So what it's talking about here is report very good health. Well, if you're living maybe in the city and you have a very stressful job, then your health might be lower. So there are other things that could affect your health instead of just your distance to the coast. Okay? All right. So now that we understand that when we create an experiment, we could have these lurking and confounding variables, we want to actually design the experiment. So there are 3 types of design experiments we're going to talk about. Completely randomized design, randomized block design, and then matched pairs design. Okay? So these are the 3 that we're going to talk about. All right. So when we have an experimental design, super important, all experimental designs have 4 key components. Okay, the first one has to be comparison. So for us to actually do an experiment, we have to compare different things. We want to make sure we're using a design that compares 2 or more treatments, all right? And this is going to be a key word, where we are exposing a treatment. We need to make sure that the groups we're comparing don't differ greatly. Before our experiment begins, or we can have bias. So let me give you an example of this. If we wanted to do an experiment on who is stronger, soccer players or basketball players. So if I looked at this, soccer players and basketball players, well, what I didn't say is that we have female soccer players and we have male soccer players and we have female basketball players and male basketball players. So if we're looking at just strength, we know right away what's going to happen. The males are going to be stronger. So this is not a good comparison because they differ greatly. So we would want to change our experiment. We want to include, especially, we want to compare the strength between just females or just males. So to compare different treatment groups, we set up different factors and levels. And so what this looks like is a factor. A factor is the explanatory variable in the experiment and is deliberately manipulated in the experiment. You've done this with scientific methods since you were in like 3rd grade. So the factor is what we're going to call the explanatory variable. It's the independent variable. The levels are the various groups that the factors take. So, for example, we are going to deliberately manipulate something, and so the outcome are going to be what those various groups, the factors that those various groups take. So the combination of the levels from the factors are all going to be the experimental units, and we call those units the treatments. So here's an example of how this all goes together. So a researcher wants to test the effects of a combination of diet and exercise on weight loss. The groups will have less than 2,000 calories a day, between 2,000 and 3,000 calories a day, and over 3,000 calories a day. So I have 3 different groups, okay? The exercise groups will have 3 or less periods of exercise a week, or 4 or more periods of exercise a week. All combinations of treatments will be examined. How many treatments, factors, and levels are there in this study? Well, the factors are going to be diet and exercise. So I have 2 factors. The levels are going to vary depending on whether we do diet or exercise. So what we might have is less than 2,000 calories, between 2,000 and 3,000 calories, and then greater than 3,000 calories. All right? And our exercise is going to be less than 3 days per week or greater than 4 days per week. So these are our different levels. So if I want to look at treatment options, here's what I have. I have a less than 2,000 diet with 3 days of exercise and 4 days of exercise, or a 2,000 to 3,000, 3 days and 4 days, and then greater than 3,000, 3 days and 4 days. So what I have here are these are the different treatment groups. So these are my different treatment groups, and I have 6 options. I have 6 different treatment groups. So we have the factors, diet and exercise, the levels, which is everything independently, and then my treatment groups are going to be these combinations of diet and exercise. Okay? All right, so the next part of an experiment that we have to have is going to be randomization. And you've heard that word so much during this unit. Everything is going to be randomized. So randomization must be incorporated in either the selection of the experimental units, and remember the experimental units is whatever we're testing. So it could be people, it could be plots of land. So when we do this randomization, this is uncommon because we have to get consent before we say, hey, we're going to put you in an experiment. Or the distribution of the experimental units into treatment control groups. And this is the one that we use more often. So the distribution of experimental units and control groups. And so normally what happens is this distribution is normally more likely because people, and the reason is because people agree to the experiment. All right, so we can only compare the groups when they're as similar as possible. We talked about that. Randomization produces groups of the experimental units that we expect to be similar in all respects before the experiment begins or before the treatment is applied, and therefore the measured differences must be due to either the treatment or by chance of random assignment. So when we see something, we need to make sure that it's either due to treatment or chance of random assignment. Okay, next thing that we have to have in our experiment is a control group. So control group is a group that is treated the same as the treatment groups, but does not receive the treatment. So it's just this benign group that we're going to look at the treatment results, and we're going to see if this group had any effect. And so what happens is the group should not know they are not receiving the treatment. And so this is what we call the control group. Normally these would be people that agree to the experiment, but then they don't get any treatment. The control group is the baseline. Our experimental group has only changed one thing, and that's the explanatory variable. So this is the baseline, and the experimental group is the one that gets the treatment. Okay, now this, when we do this, this reduces the variability in the response variable. Now, I'm going to add something here because a minute ago I said that every experiment had to have all 4 components. However, not all experiments have a control group. And one of the reasons is because a lot of times this is going to be ethical. So let's say we want to, I don't know, I'm trying to think of an example right now. We want to look at the results of I don't know. Let me think of a good example. I wasn't thinking of one right now, but I'll think one. So when we don't have a control group in our experiment, we just need to say that. We say we will not have a control group in our experiment. All right? Okay, let's keep going. Last one. Last one that we have here is replication. So we have to use enough experimental units, so there have to be enough people or plots of land in each group so that any differences of the treatments can be distinguished from chance differences between the groups. So in stats, replication means using enough subjects. So you want a big sample size. We don't want to do an experiment on 2 people. So even with control, we know that we have natural variability. So even if I was doing something like testing a new medication and we see results, those results might have a lurking or confounding variable that we don't even know about. We would like to see units within the treatment group respond similarly to one another, but differently from the units in the other groups. That makes sense. If you're giving medication to one group and not the control group, we want to see those 2 groups respond differently. And if we assign many individuals to each treatment group, the effects of chance will average out. And that's why we want to have a larger sample size. Okay, let's keep going on actually designing the study now. All right, so we have 3 different types of designs we're going to do. So this first one is completely randomized. So in completely randomized design, experimental units are assigned to the treatments completely by chance. So we're going to do something like a simple random sample. So something like an SRS or pull out of a hat or something that's completely random. When describing a completely random design, it's important to identify when the random design occurs. So when are we going to do this random assignment? In an experiment, we're going to usually label this as RA, for random assignment on our diagram. And then we're going to describe how to do the random assignment. So is this going to be a random number generator? Is it going to be pull people from a hat? How did we do our random design? And we've already covered that in this unit, so you know that there's a lot of different ways we can do this. We can even go in and get real specific and say, we're going to stratify, we're going to cluster, we're going to whatever that looks like, okay? All right, so here's what this looks like when you create a design block like this. The first thing that we're going to do is identify the sample. So we have a group of people, I don't know, 100 people, whatever. And then we're going to do random assignment. So this is random assignment. Right? So what we have to do here with the random assignment is we have to say how, so maybe a random number generator, and we have to say group sizes. Then the next thing that we're going to do is identify the treatment. Now, what we could do is these 2 could go backwards. We might identify the treatment and then based on our treatment, randomly assign to each of our treatments. And this may even be if we have a control group, if we have, so these 2 are kind of interchangeable. And then we always want to compare results. So this is really kind of our draw conclusions. All right, so when randomly assigning subjects, split them as evenly as possible. So that's our group size. And then sometimes the groups have to be uneven, but they should not be significantly uneven. All right, so let's practice this right here. It says, medical professionals want to study how different brands of prenatal vitamins can impact iron levels of expecting mothers through pregnancy. The study follows a sample of 50 expecting women from 4 weeks of pregnancy through their delivery. So 50 pregnant women. The 5 different brands are, so these are the different brands of vitamins that they took, 3, 4, 5. In this experiment, a control group is not allowed. Why do we not have a control group? Oh, here's a perfect example of that. And so what does this look like? So I'm going to draw my experimental diagram right here. So I'm going to start right now with identifying the sample. So I have 50 pregnant women. And I, in this case, am going to randomly assign into groups. All right, so here's my random assignment. And now I have to identify my treatment group. So my first treatment group is going to be Rainbow Light. My second treatment group is going to be Nature Made. My third one is going to be Mega Food. My next one's going to be Ritual. And then my last one down here is going to be Nordic. So those are my different treatment groups. Now, I kind of breezed over this, but why are we not going to have a control group? Well, if we're talking about pregnant women and the effects of prenatal vitamins on pregnant women, we don't want to have a group that doesn't receive any prenatal vitamins. That would go back to what I said about having something be ethical. So this is a perfect example of why we do not have a control group. So you might want to say no control, because all pregnant women should take a prenatal vitamin. Okay, now what are we going to do? Our last step here is we're going to take all the data and we are going to compare iron levels. And that's really what we're looking for, right? Set up here, we want to study the impact of iron levels. So our compare results are compare the iron levels. So this is what my design experiment would look like, but we're missing this random assignment piece. And that is what's on the next page here. So the next page says, how would you randomly assign 50 pregnant women to the different treatments? So we have a number of different ways to do this. This needs to be pretty precise, and it's going to be really wordy. So let's just say I'm going to assign each context pregnant woman with a number from 1 to 50. Randomly generated numbers in groups of 10 that cannot be repeated would be, I would say, actually I should say in a group. So randomly generated numbers in a group of 10 that cannot be repeated would be assigned to Rainbow Light. All right, then I would say generate 10 additional random numbers, non-repeating, and assign to Nature Made. And then I would say repeat random generation until all groups, or you can say all women, are filled with 10 subjects. All right, so let me read this through. Assign each pregnant woman with a number from 1 to 50. Randomly generate numbers in groups of 10, or in a group of 10 that cannot be repeated, and assign those to random light. Generate 10 additional random numbers, non-repeating, and assign to NatureMade. Repeat random number generation until all groups are filled with 10 subjects. So, very wordy. You know, I don't like to write, but definitely when you talk about your random assignment, you have to be super wordy so that they understand that if you were running this experiment, you could read this and you could follow the directions so that your random assignment was accurate. Okay, next thing that we're going to do is we're going to talk about blocked design. So random block design. So that's another option that we have. So here, experimental units are divided into groups, we call those blocks, prior to the experiment. So this reduces the effect of identifiable attributes of the subjects that cannot be controlled. So maybe go back to my example of soccer and basketball, and we would separate this out into women and men, okay? So blocking is used to control the factors you see. So these are things that you know, like gender. Randomization helps balance the ones you can't see, all right? So, like for example, if we talk about this vitamins thing, if we just stick on with this vitamin, it might be that you have, you block this into age. So are younger pregnant women more likely to absorb the iron than the older pregnant women? All right, so this is what blocking looks like. So you're still going to identify the sample. You're going to block into units. You're going to do your random assignment and then identify treatments, compare results, and then combine results. All right, so let's try this out, see how it goes. Does cold water or hot water clean laundry better? Okay, well right away we can see that we can block this. We're not saying just our water. We want to know specifically cold water and hot water. Does the laundry color, okay, matter when cleaning with hot or cold water? You have 4 piles of dirty laundry to test these questions. Describe and design a completely randomized block design. So, identify my sample. I have 4 piles of dirty laundry. So we have a couple of options right here. What I don't know is, of these 4 piles of dirty laundry, how much of this is light colored and how much of it is dark colored. So we're gonna hope that this is about the same. So what I'm gonna do is I'm gonna say I want 2 piles of whites or lights, and I want 2 piles of darks. Okay, so this is my block of my unit. I'm going to look at whites and I'm going to look at darks. Now, here I'm going to do my random assignment. Now remember, we still have to go back and talk about what random assignment is going to look like, but this is my random assignment. Now, within my random assignment, now with whites, I have to evaluate cold water, and I'm going to evaluate hot water. I'm going to do the same thing with my darks, cold and hot. And then with this, I'm going to compare the results, what gave me better data. And then the last step is I'm going to combine. So, and it might be that when we combine the results, we have 2 different outcomes. So white cleans better with hot water, and dark cleans better with cold water, right? We might just say that. So when we talk about our random design on this, What's important is that we identify our random assignment. So how are we going to do this? So I'm going to randomly assign, I'm going to do something different on this. I'm going to randomly assign whites as heads and darks as tails, and flip a coin. To determine which block gets cold water and which gets hot water. Right, and then again, this, I actually did not do very good on this. So can I follow the instructions on this? This is what I need to ask myself. Can I follow these instructions to be able to do this? Okay. Let's see. I think we have one more. Oh, I guess that's where I was supposed to write this. Oh, well, hold on. Let's add something here. So we can do a random number generator, and we could also do something like a coin. We could do something like a dice. It doesn't have to be a random number generator. So just remember that when you do your random assignment. All right. We'll come back to this popcorn one. We might do something with that in class, actually, now that I think about it. All right, matched pairs. So this is our third one. And I know this video is getting long, so I'm going to try to go quick here. In this design, each experimental unit received both the treatment and the control. All right, in this design, each experimental unit receives both the treatment and the control. The order that the treatment and control assigned should be random. So they both get the treatment and the control, but we don't know what happened first. If subjects are used, they should not know which treatment or control they are receiving. So what comes first? Another way to do this design is to pair units so that they are as similar as possible, and then every pair receives both treatments randomly by assigning one treatment to one member of the pair and then assigning the other treatment to the second member of the pair. We would do something like this if we were dealing with maybe twins, right? Where everything is the same, but they're still different. Okay, so let's look at an example. I think that's what I have here as an example. So, does listening to classical music improve concentration during a task compared to not listening to any music? A group of 30 student volunteers will complete a series of logic puzzles, once by listening to no music and once by listening to classical music. The logic puzzles will be slightly different for each administration of the treatments. So, here's what I know. I'm going to start with 30 subjects, 30 people. And what I'm going to have is, within this, I'm going to have my first person, and then I'm going to have my second person, and I'm going to have my third person, all the way down here to my 30th person. All right? Now, I am going to do a random assignment, and this random assignment is going to be classical, and then no music. And then after this, I'm going to do no music, and this one's going to get classical. All right. Now, here I go into compare, and then the last step is going to be down here when I take everything and do combine. Now, what does this look like? This is also going to be random assignment, and it's still going to be classical to no, and then no to classical. then I compare, and then combine. Okay, so when I have something that looks really big like this, I don't have to write every one of these, but I have to show that it's going to be consistent through this whole thing. Now, what's important on this is going to be this, random assignment. So how do you randomly assign this? So what I would do on this is maybe I will randomly assign, actually, you know what? I'm going to write this out real quick, and then just to save time, and then pull it back up, and then you can pause the video. All right, so here's what I put together. I will randomly assign each treatment within each individual subject. That's what I show here in my diagram. For subject number 1, I will flip a coin where heads is classical music first and no music second. Tails would be no music first, followed by classical music. I would repeat this for each of the remaining 29 subjects. Now, what you might say is, instead of flip a coin for classical music, you might just say, pull out of a hat, and it's either going to be classical or no music. And then you would say that you would put the paper back in the hat, and that you can or you will have a replacement, meaning you're going to pull it, put it back in the hat, you will have replacement, and then after you have the replacement, you're going to continue or repeat this procedure for the remaining 29 subjects. Or in this case, you could also say students, because that's we know what the context is. They're students. Okay? So what do we want to do here? We want to draw the diagram and then explain the random process. Both of these two things are going to be important as you do this. All right, so vocabulary. So what's important here is that you don't mix the language of experiments, so that's what we're doing right here, with the language of sample surveys or observational studies. So you would lose credit by saying use a randomized block design to select the sample for this survey, or randomly assign the treatments using 3 different strata. So strata is something that goes to survey and not an experiment. So make sure, we're going to do more in class with vocabulary. Super important. All right, last concept that we have to talk about is inference. And you know what? I'll do a separate video for inference.